Section 3.2, Rolle's theorem and the mean value theorem. Rolle's theorem, which is attributed to Michel Rolle, he's a French mathematician. It was published in 1691. Here are the details. Given a function that satisfies the following three hypotheses. The first one, f being a continuous function on the closed and bounded interval AB. Second, f being differentiable on the open interval AB. And third, f of A, the lower bound, is equal to f of B, the upper bound of the interval. Under these three hypotheses, the following happens. There must be a number c in between a and b where the function f prime vanishes. Okay, so one more time. If you have a continuous function on the closed and bounded interval AB, and if this function is differentiable on the interior of that interval, so on AB open, and f of the endpoints are the same, so the image of the endpoints are the same of the interval, then there must exist a number c in between a and b such that f prime of c is 0. The proof of this theorem requires the extreme value theorem. If you remember, the extreme value theorem says if the function is continuous on the closed and bounded interval, then it must attain its maximum. There must exist an absolute maximum, absolute minimum, and these extrema are attained within that closed and bounded interval. I'm going to just say a few words about the proof. Look, if the function f is a constant function, obviously all three happen, so such a function is a possible function. If the function is a constant, then certainly f prime at any point c in between a and b is 0. So this number c that exists in the conclusion of Rolle's theorem can be any number in between a and b. If the function is not a constant, so either there exists a number x in AB such that f of a is smaller than f of x, and as such, there must exist an absolute maximum in this context in between a and b, open, by the extreme value theorem, and as such, this maximum is gonna be a local one, and by Fermat's theorem, f prime of c is 0 because the function is differentiable, right? And the last case, if there exists a number x such that f of a is greater than f of x, as such, the absolute there exists an absolute minimum in between a and b, and this absolute minimum is going to be a local one. By Fermat's theorem, since the function is differentiable, that conclusion is going to follow. Again, if you would like all the details of the proof of Rolle's theorem, please just post a note on the forum, and I'll be happy to either give you the details via a writing a note, or I can record a video for it. But I just mentioned the ingredients of that proof. Let me show you why Rolle's theorem is intuitively plausible. Consider the following situations. Consider all of these, let's consider all of these figures. Let's consider the first one, the constant case. Obviously, a function that's constant. Let me zoom out a little bit here. Obviously, a constant function verifies all three conditions, and you can see that at any point between a and b, let's say at this point c1, the derivative is 0. correct? So at any point between a and b in this context, there exists, I mean, any number between between a and b, its derivative, the derivative of the function at this number is going to be 0. Take a look at this function. This function is not constant, and it verifies all three conditions. It's continuous between a and b. It's differentiable. It's a smooth function. There's no cusp or kink or discontinuity anywhere, or infinite tangent. And the last condition, f of a is equal f of b. F of a is equal f of b. Then somewhere in between a and b, at this number c in this case, the function is gonna kind of reach an extremum. In this case, it's a maximum, right? So the function has a horizontal tangent at c. For this graph, this is a function which is continuous between a and b, and it's differentiable between a and b. It's a smooth one again. So there exists, and the last condition, f of a is equal to f of b. So it starts at the same height it ends. Then there exists at least one c in between a and b, such that the function is gonna have a horizontal tangent. In this case, that happens twice, at c1 and c2. And this last picture, also this picture verifies all three conditions of Rolle's theorem, and as the conclusion of that theorem, I mean, it's guaranteed that I'm gonna be able to find a number c in between a and b where the function is gonna reach a minimum in this case. Okay, so the function is gonna have a horizontal tangent at some number c. In this case, that's the c we're talking about. That's the c that the theorem is alluding to. All right. Example. Let's apply Rolle's theorem to the position function of a moving object. If the object is in the same place at two different instants, let's say at moment A and at moment B, that means that f of A and f of B are the same. And as such, the Rolle's theorem is going to be applicable, and it tells us that at a moment C between A and B, f prime of C is 0, which means the velocity at this moment C is 0. You can see this intuitively by just thinking about a ball thrown upward. If you throw it upward, certainly, since it's gonna reach that height from which you threw it, somewhere in between the initial moment, the moment you tossed it and the moment it reached that height again, certainly the velocity of that ball vanished, which means it's reached a maximum and then it's coming back. Okay, here's a problem. Prove that the equation x cubed plus x minus 1 is equal to 0 has exactly a real root. Exactly one real root. What's a root again? A root is a number that solves the problem, that solves the equation. So prove that this equation has precisely one number x that you can plug in and you get 0. All right, how are we gonna do this? I'm gonna go to a blank page. So and then I'm gonna copy it. So x cubed plus x minus 1 equals 0. Let me write that down. So this is example. We want to prove that the equation, what is it? X cubed plus x minus 1 equals 0 has exactly one real solution. So the way we're gonna do it, we're gonna show that this equation has a solution, has a root, and we're gonna show that this root is unique. So we're gonna go in 2 steps. Step 1, so first, we show the existence of such a solution. Of such a root. We're talking about the existence. And then as a next step, we talk about the uniqueness of that root. So how are we going to talk about the existence of this root? I'm going to invoke the intermediate value theorem. What does the intermediate value theorem say? It says that if you have a function which is continuous between a and b, and f of a and f of b are not the same, then no matter what height you take, n, in between f of a and f of b, right? No matter what n you take in between f of a and f of b, there exists a number c, or alpha, in between a and b such that f of alpha is equal to n. Correct? This is the intermediate value theorem. In particular, if this horizontal axis is that line, so if the function crosses the x-axis, then somewhere the function, one more time, if the function goes from one side of the x-axis to the other, let's say from the lower half plane to the upper half plane, or the upper half plane to the lower half plane, then somewhere it must cross the x-axis. Correct? So what I'm talking about is a graph like this. If the function goes, let's say, from this level to this level, and continuously, so somewhere the function crossed the x-axis. So there exists a number here so that f of that number, let's say this is the alpha, f of that number is equal to 0. If I manage to show that the function crossed or passed from one half plane to the other. All right, so this is the idea here. This is what I'm gonna do to show the existence of the solution. So I'm gonna erase this discussion. Okay, and let's show it. So we appeal to the intermediate value theorem, okay. How about I ask you to evaluate this, let's call this guy f of x. How about I ask you to evaluate this function at some number? How about f of 0? What's f of 0? Well, it's 0 cubed plus 0 minus 1, which is minus 1. So this is negative. And how about I ask you to evaluate f at 1? Well, f of 1 is 1 cube plus 1 minus 1, so it's 1 cube, which is 1. So that's positive, correct? So the function between 0 and 1, it went from negative to positive. So the function at 0 it was at negative 1, and at 1 it's at 1. So this is 1 here, and this is 0. So it went continuously in between the two. Why it's continuously? Because look at f. F is a polynomial, right? So it's a continuous function everywhere, because remember, for polynomial functions, they are continuity and being well defined are synonymous, right? So wherever f is defined is continuous, because f is a polynomial. So the function f is defined everywhere, and hence it's going to be continuous everywhere, in particular in between 0 and 1. The function is going to be continuously going from this point to this point. As such, it has to cross, by the intermediate value theorem, it has to cross the x-axis somewhere. So let's record this. Okay. Since f is a polynomial, it is continuous everywhere on R, in particular on 0, 1. So I verified the conditions of the intermediate value theorem, and as such, there must exist a number alpha, where f of alpha is 0, meaning the function crosses the x-axis. So thus, by the intermediate value theorem, there exists an alpha in between 0, 1, such that f of alpha is 0, where the function crosses the x-axis. All right, so what have we shown so far? We've done with the existence. So we know now there exists a number, alpha, that does this job. F of alpha is equal to 0, meaning alpha cubed plus alpha minus 1 is equal to 0, right? This is what we've shown. And this number is somewhere between 0 and 1. Okay. Now the question is, show that this number, alpha, whatever it is the only one that does the job. Is the only number, so that if you plug it in here, you get 0. There are no more than this alpha. So now we're gonna show the uniqueness part, right? Okay, let's zoom in. Secondly, we prove the uniqueness of the root. Correct? This is what I want. All right. So how do we show the uniqueness of the root? I'm going to assume I have more than one. I'm going to assume I have 2. So let's assume, to be more precise, I wanna I want to solve. I want to analyze it by contradiction. So I'm gonna do the following. By contradiction, we assume that I have more than one root. So we assume that there are two roots for the function f of x. So there exist, let's give them names. How about t and s, such that f of t is equal to 0 and f of s is equal to 0, right? So one more time. I'm assuming, remember, I'm showing the uniqueness of the root. I know that the root exists. At least one root exists. This is what we showed in the ping discussion over here. Now we're gonna show that this number alpha is unique. I'm gonna assume I have more than one. Let's call them t and s. And I'm gonna reason by contradiction. I'm gonna show you at the end of the day that t and s, there exists no such a thing t and s. Two different things t and s. There must be the same. Okay? So to be precise here, let me say, so there exists t and s such that t is not s, so they are distinct, and f of t is equal to 0 and f of s is equal to 0. Correct? So I suppose I have two distinct roots, and at the end of the day I'm gonna show you that this is not possible. I'm gonna get a certain contradiction. All right. Well, if f of t is equal to 0 and f of s is equal to 0, this means f of t and f of s are the same. Correct? So the f of t and f of s are the same. Let me go to the first page. So I'm verifying the third condition of Rolle's theorem. F of t and f of s are the same. Let's check the other two conditions. Remember our f? It's a polynomial, so it's continuous everywhere. In particular, it's going to be continuous on the closed and bounded interval ab, which is in this case st, whichever is smaller, the s or the t. And f is also differentiable on the open interval ab, st, because f is a polynomial. So all three conditions of Rolle's theorem are going to be verified, and as such, this conclusion is going to be valid, which means somewhere between s and t, the function f prime is going to vanish. That's the conclusion I can say by Rolle's theorem. Okay. So let's go back to this. So, so since t and s are not the same, I'm going to assume that one is smaller than the other. How about we say that t is smaller than s? Right? Since t and s, I'm assuming they are distinct. They're both real numbers. Certainly one is smaller than the other. Without loss of generality, I can think about t as being the smaller one. All right. So also, f is continuous on ts. Why is continuous on ts? Because the function is a polynomial, right? And a polynomial is continuous everywhere. So, since f is a polynomial. And f is differentiable on the interior of the closed and bounded set ts, so in the open set ts. Sorry about that, t comma s. Again, since t is a polynomial. So all three conditions of Rolle's theorem are verified. Let me highlight them for you. This is equal to that. So f of A is equal f of B. F is continuous on AB, and f is differentiable on the interior of AB. So I can now apply Rolle's theorem. So then by Rolle's theorem here, I'm applying it. What can we infer? We infer that there must exist a number between T and S such that f prime of C is 0. Correct? This is what Rolle's theorem tells us. There exists a number C between T and S such that this happens. All right. What's f prime of C in this case? What's f prime of X? This is f of X, x cubed plus x minus 1. So what's f prime of X? It's 3x squared plus x plus 1 minus 0. One more time. 3x squared plus 1 is f prime of X. So f prime of C is going to be 3c squared plus 1. So this guy here is 3c squared plus 1. So this guy here is 3c squared plus 1. Correct? So, i.e., there exists a number C between T and S such that 3c squared plus 1 is equal to 0. This is so far what we have. Correct? And now look at this guy here. 3c squared plus 1 is equal to 0. Can such a thing exist? Can such a C exist? 3c squared, what you know about 3c squared is at least 0, right? This guy is 0 or more. And if you add 1 to it, this whole thing is certainly at least 1. So how is it possible to be 0 then? This is a contradiction, right? That's not possible because this entity here is at least 1. And hence there's no way it goes below 1, which is it never reaches 0. So this thing has no such a C which does it. Contradiction. That's the contradiction I was looking for, right? What does it mean? It means that our assumption was not correct. And what was the assumption? Our assumption was that there exist two distinct roots for the function f. So the function f cannot have two distinct roots, and as such, the root must be unique. This shows the uniqueness of the root. So therefore, the root of f of x is unique. So root of f of x is the same thing as saying the solution of f of x equals 0, right? Must be unique. Okay, exists and must be unique. Because remember we showed the existence in the pink discussion above, and is unique. Answering the question that we wanted to do, right? The question was, prove that there exists one and only one real solution to this equation. We just showed the existence of it and the uniqueness of it, and as such we can conclude that that root exists and is unique. All right, very good. So we're done with this exercise. This is what we did, this exercise. Let's move on now to the mean value theorem. This is attributed to Joseph Louis Lagrange. And Lagrange, I think he lived in the 18th and 19th centuries. The mean value theorem reads as follows. Given a function verifying now two conditions, these are the two conditions of Rolle's theorem. The first two conditions. You don't need the third one anymore. So if given that the function is continuous on the closed and bounded interval AB, and the function being differentiable on the interior of AB, there must exist a number C in between A and B such that f prime of C is this quotient, f of B minus f of A is equal to B minus A. Equivalently, if you multiply through by B minus A both sides, you get f of B minus f of A is equal to f prime of C times B minus A. Okay. I want to just highlight the fact that the mean value theorem encompasses, is in some way stronger than Rolle's theorem. It looks like it, at least. Stronger than Rolle's theorem. Why? Because what if you assume that this holds and you assume in addition that f of A and f of B are 0. If f of A and f of B are the same. If f of A and f of B are the same in addition to these two conditions, then this numerator is 0. And hence 0 divided by a non-zero entity is 0, which means f prime of C is 0. And hence you get Rolle's theorem for free. So it looks like the mean value theorem is a stronger theorem than Rolle because it implies it. If in addition to the assumption you have in the mean value theorem, you assume the third one, the third condition in Rolle's, then you get the conclusion of Rolle's. So the mean value theorem implies Rolle's theorem. However, the proof of the mean value theorem actually requires the Rolle's theorem. And again, if you want me to show you the proof of the mean value theorem, I'll be happy to discuss it, but post something on the forum on Canvas to allow me to realize that someone is interested in the proof. So as I said, the mean value theorem, in the proof of that theorem, Rolle's theorem is the active ingredient there. So what this says, the mean value theorem and Rolle's theorem are actually the same. They are exactly the same thing, but they look different. Okay, they are equivalent. This is what I mean. All right. What does this mean? Let's give some geometric interpretation of that theorem, of the mean value theorem. Do you remember what this guy is? F of B minus f of A over B minus A. This is the slope of the secant line joining the point whose coordinates are A f of A and B comma f of B, right? And this guy f prime of C is the tangent line to the curve f at the point C. So what this theorem is saying then is that somewhere under these conditions, somewhere between A and B, the tangent line to the curve at that point C that exists is equal to the slope of the secant line joining the 2 points A comma f of A and B comma f of B, as you see here on the picture, right? Somewhere between A and B, so at C, the tangent line to the curve at this point C, whose first coordinate is C, is going to be parallel to the secant line, right? Being parallel means they have the same slopes. This is one example, and this is another. Look, here I have two places, C1 and C2, where the tangent lines are parallel to the secant line. The mean value theorem is the nature of the conclusion of the mean value theorem is similar to the nature of the conclusion of the Rolle's theorem, which is also similar to the nature of the conclusion of the extreme value theorem and the intermediate value theorem. Those theorems are only about the existence of something, verifying a certain property. They're all existence theorems, right? They don't tell you, however, they don't tell you how to find that number that the conclusion is trying to is alluding to, and they don't tell you how many of these guys the function exhibits. So what it tells you, what all these theorems tell you, they only tell you the existence of such a thing. Okay. So here in this, for this picture, apparently there exists just one point at which the tangent to the curve is going to be parallel to the secant line. Here there exist 2 points, C1 and C2, where the tangent lines are parallel to the secant line joining A and B, right? A here has coordinates A comma f of A, and B, capital B, it has coordinates little b and f of that little b, right? Okay. Let's look at this red note I have here. In terms of rates of change, the mean value theorem, MVT for short, implies that there must be a point in AB at which the instantaneous rate of change, right, f prime of c is the instantaneous rate of change, is equal to the average rate of change over the interval AB, correct? For instance, if you want to take a concrete example, if you have a car that traveled 180 kilometers in 2 hours, so 180 kilometers in 2 hours, this means that you have here 180 divided by 2, which means 90. So what the mean value theorem says, somewhere at some point between those 2 hours, the velocity of that object, of this car, was 90 kilometers, at least once. And this is intuitively correct, right? If you know that this car traveled 180 kilometers per 2 hours, then somehow or somewhere, this, at least once, this speedometer must have read 90 kilometers per hour, at least once, right? By at least once, it means the existence of at least a moment where this happens. Okay. All right. Let's take a look at the next example. To illustrate the mean value theorem with a specific function, let's consider f of x equals x cubed minus x, little a to be 0 and little b to be 2. Since f is a polynomial, it's a polynomial, so it's continuous everywhere and it's differentiable everywhere. So in particular, that function f is continuous on the closed and bounded interval 0, 2. It's differentiable on the interior of 0, 2. Therefore, the mean value theorem is applicable. Why? Because I just verified the 2 conditions of that theorem, these guys. So what can you say then? There exists a number c such that f prime of c is going to be f of 2 minus f of 0 divided by 2 minus 0. Or equivalently, f of 2 minus f of 0 is equal to f prime of c times 2 minus 0. Like this, right? This is what the theorem allows us to conclude. That's the conclusion. This conclusion or this conclusion, they are equivalent, right? So I chose to write it this way this time. All right. However, in this context, I can get my hand on that number c. I can evaluate f of 2. F of 2 is 2 cubed minus 2, which is 6. F of 0 is 0 cubed minus 0, which is 0. And f prime of c, well, f prime of x is 3x squared minus 1. So f prime of c is 3c squared minus 1. So this whole thing becomes 6 minus 0, so 6 is equal to 3c squared minus 1 times 2. And 3c squared minus 1 times 2 is 6c squared minus 2. And if you solve for c, you get that c is plus or minus 2 divided by square root of 3. So 1 positive, 1 negative. But in our discussion, the c is between 0 and 2. So the c we're looking for is the 2, the positive part, the 2 divided by square root of 3. And if you go to Desmos, actually, and you try to graph this function, this line here, that at this number c, that's the tangent line that's going to be parallel to this secant line, joining the origin, right, 0, 0, and 2, 6. Okay. Another place where we can use the mean value theorem is we can derive information about the function from information about its derivative. This is another place where the mean value theorem, this is the main significance of the theorem. Let's take the following example. Suppose that f of 0 is minus 3 and f prime of x is at most 5 for all values of x. The question is, how large can f of 2 possibly be? Okay, so let me take this all the way to the last page here and paste the question. So again, I have that f of 0 is minus 3 and f prime of x is at most 5 for all x. So if you're given that f prime of x is at most 5, you're given that f prime of x exists for all x, right? So the function f prime exists for all x. So we are given f prime of x exists for all x, implies actually is equivalent that f is differentiable for all x everywhere, and every differentiable function is continuous, right? This implies that f is continuous for all x. Oops. Correct? The function f is continuous for all x. So you have that the function is differentiable for all x and it's continuous for all x. Well, in particular, it's continuous on the set or the closed bounded interval 0, 2, and it's differentiable there as well. Correct? Because it's differentiable and continuous everywhere. So hence f is continuous on 0, 2, and f is differentiable on the open set 0, 2. So the mean value theorem is applicable because you have that f is continuous on the closed and bounded interval and differentiable on the open, on the interior of that set. So these two imply, by the mean value theorem, they imply by MVT, they imply that what? There exists a number c between 0 and 2 with the property that f of b minus f of a is equal to f prime of c times b minus a, right? This is what the mean value theorem implies or says. That's the conclusion of it. All right. What does it mean? So there exists c between 0 and 2 such that f of 2. Okay, what's f of 2? Let's actually write it immediately. What's f of 2? Well, it's the thing that you want to find. So f of 2 minus f of 0. What's f of 0? It's minus 3. So it's minus 3 equals f prime of c times 2, right? F prime of c times 2. What's the question again? We want to find how large f of 2 can be. All right. That's the same as f of 2 plus 3 equals 2 times f prime of c. So this means that f of 2 is equal to 2 times f prime of c minus 3, right? Because on the left side it was plus 3, so to move this way it becomes minus 3. Am I correct? All right. Now, what do you know about f prime for all x? F prime, the derivative of f at any point is at most 5. So what can you infer about this guy? How large can this guy be? It's right there. At most it can be 5, right? So this is at most 5. So what can you say about twice that thing? How large can this whole thing be? It's twice 5, which means at most 10. So this guy is at most 10. How about the whole thing? It's at most 10 minus 3, which is how much? Which is 7. Right? Because this whole thing is at most 10 minus 3, and 10 minus 3 is 7. So f of 2, so now look at this, f of 2 is at most 7. So how large can f of 2 be? The largest it can get is to 7 by the mean value theorem. Make sense? All right. Let's now go to that page that we left. Where were we here? Okay. All right, so we answered this question. All right, the last two exercises in this section, they are, with the help of the mean value theorem, we can establish some of the most basic facts of differential calculus. One of these are mentioned on the next couple exercises, and the rest are in the future exercises, future sections. Let's start with exercise 1. If f prime is 0 for all x and in an open set AB, open interior of a closed bounded set AB, then f must be a constant there. This is actually on page 180, number 78. So one more time. If f prime is 0 in the interior of a bounded set and closed, then the function f must be a constant on that set. Okay, so let's write that down. Let's zoom in. Okay. So we have if f prime of x is equal to 0 for all x in AB, we need to show that f is constant on AB. Right? This is the question. All right, so the way we're going to do it is I'm going to show that at two distinct elements in AB, the function has the same value. Okay, so we show that, so we choose two random elements in AB. Let's call them, I don't know, Z and T. So let Z and T be inside, so be in AB. say that, I mean, since they're not the same, I should say they're not the same, such that z and t are not the same. Since two numbers are not the same, then one is smaller than the other. So without loss of generality, I can assume that, let's say, z is smaller than t. Because otherwise you can just take t to be smaller than z, and the process is the same while if you rename z to be t and t to be z, right? So it's the same thing. Okay. Okay, so what I want, let me write it in a different color. So we want to show that, oops, we want to show that f is constant on AB, meaning f of z and f of t are the same. If I manage to show this, I'm done, right? Because z and t were randomly chosen in the set AB. So this means that f is going to be the same for any numbers z and t randomly chosen in AB. As such, f must be a constant. Okay. All right. Let's show it. So you know that f prime is 0, so you know that f prime exists on AB, right? So you know that, so we know f prime exists on AB. This is what we're given, right? And if it exists on AB, then it's going to exist on ZT. Why? Because ZT, this set, this interval ZT, is a subset of AB, Z and T being inside A and B, correct? So this is A, this is B. Z and T are within that interval. So maybe Z is somewhere here and T is somewhere here. So that's the interval I'm working on. If f is differentiable, right? Because they told us f prime of x is 0, which means f prime of x exists, which means f is differentiable on AB. So if f is differentiable on the larger set, certainly it's differentiable on the smaller one. That's what I said here, correct? All right. And what do we also know? We know that f prime, since f prime is differentiable on AB, it has to be continuous on that set, because every differentiable function is continuous. So we also know that f is continuous on the whole thing AB, open. So certainly it's going to be continuous on the small one, ZT, closed. Remember, Z cannot be A by choice, right? Z was chosen to be inside AB, so Z is not A and T is not B. So this, I can close that thing inside. Okay. Let me take this, move it a little bit for you. Okay. All right, so what do we have? We have that f is continuous on the closed and bounded set ZT, and we know that f is differentiable on the open, the interior of the set ZT. Thus, by the mean value theorem, there must exist some number c between ZT, right? That number c is going to be somewhere here, with the property that f prime of c is equal to f of t minus f of z divided by t minus what? T minus z, right? Correct? All right. And now let's put this condition that we have in action. We know that f prime of x for all x in AB, in AB, f prime of x is 0. Well, this c is inside zt, right? So certainly it's inside AB by choice of z and t. So c, that number c is between a and b. So I can choose that x to be c and get f prime of c has to be 0, right? So f prime of c must be 0. So this guy is 0. So this guy is 0 by assumption. All right. And we're done, right? Because if this guy is 0, well, this guy happens to be equal to this quotient. And the quotient is 0 as long as the numerator is 0. So this means, okay, let me finalize it here. So therefore, f of t minus f of z, the numerator must be 0. Why? Because this quotient is 0 at the end of the day. And the quotient is 0 exactly when the numerator is 0, which means f of t must equal f of z as wanted. This is what I wanted. Right? Why? It's right there. This is what I wanted. So, and at this point we're done because z and t were randomly chosen in AB, and f takes the same value at those two arbitrarily chosen points. So f must be a constant on that set AB. So f must be a constant on that set AB. You can just finalize it on your own. Okay. All right. So this is a very important fact. If the function f is differentiable and has 0 as its derivative on the interior of a closed and bounded set, then f must be constant on that set. Okay. All right. Exercise 2. I'm gonna leave it for you to do, but let's read it. If you have two functions, g and h, and you know that g prime and h prime are the same everywhere on AB, prove that they differ by a constant. Prove that g and h, g minus h, is a pure constant, which means g of x is h of x plus some pure constant. So one more time. This exercise is about the following. If two differentiable functions have the same derivative on the interior of a closed and bounded set, then they must differ by a constant on that set. So this is I'm gonna leave it as an exercise for you, and the hint is use exercise 1 for a special function f, and the function f is gonna be actually g minus h. All right, so I'll leave it to you as an exercise. Consult me if you need more help. The last thing is a remark. Care must be taken in applying exercise 1. For example, take this function, x divided by the absolute value of x. If you think about it, if x is positive, upstairs and downstairs are the same, so this becomes 1. If x is negative, upstairs and downstairs are almost the same up to a change of sign. So x upstairs, negative x downstairs, this becomes negative 1. At 0, this function is not defined because I would have 0 over 0, which is indeterminate. But anyway, I cannot divide by 0. The domain of this function is everything except 0. And f prime of x is 0 for all x in the domain of the function, which means minus infinity to 0 union 0 to plus infinity. But look, f is certainly not a constant. This function is not a constant. This looks like a step, right? This is certainly not a function. So you might think, oh, I have f prime of x equals 0, but the function f is not a constant. Well, and hence I'm violating exercise 1, which we just showed. But be careful. Exercise 1 tells us that f must be a constant as long as you are talking about an interval, right? A, B. Over here, the domain is not an interval, it's minus infinity to 0, union 0 to infinity. So it's the union of two intervals. As such, exercise 1 is not applicable. Is not applicable, right? However, what's applicable, you can think about just a piece of the domain, 0, infinity, and minus infinity to 0. On these two sets, f prime is really 0, because f prime is 0 on 0 plus infinity, and f prime is 0 on minus infinity to 0. So please pay attention when you use exercise 1. It's applicable as long as you're talking on a closed, on the interior of a closed unbounded set. Even though here I use it on the unbounded, but it's not hard to actually generalize it. Okay. All right, so this is the end of this section.